Hey everyone, Mr. Anderson here, and today we're going to talk about section 7.1.1 from our CPM Common Core Algebra ebook. And specifically today we're going to move from investigating linear functions into nonlinear functions, right? And our first function family that is a nonlinear function that we come across is exponentials. Now, we do have some exposure to exponentials already from chapter 5, and today we're going to do the deep dive and take a quick peek, right? Today's going to be the first day of our lesson from 7.1.1, and we'll get to the next lesson the next day, but in the next video. The goal is to start to really take a peek at what this looks like geometrically in graphical form. We're going to utilize the help of Desmos, the student e-tool that we've got access to. So if you have access to this ebook, I definitely recommend clicking on that. We'll investigate some things together, but as play is a very natural and healthy learning experience for students, it's definitely worth your time to do that. And remember, it takes time to do some of these things. So have a little grace and give yourself some of that time. All right. In chapter 5, we started with one of our primary problems, the rabbit problem, and we saw a model that was increasing, and it modeled exponential growth. And we've got an exponential growth graph right here. It starts very, very small and increases very quickly as we move from left to right on our graph. Back in the tail end of chapter 5, we saw with I guess it wasn't the end, maybe more toward the middle, we saw the bouncy ball problem. And the bouncy ball problem gave us a different kind of model. It was still exponential, but it decreased from left to right, and it looked something like that. It was what we would refer to as an exponential decay model. And those are the two kind of graphical models that we're going to investigate here in 7.1.1. And we're going to take a look, hopefully by the time we're done, at what causes them to look the way that they look and how we can achieve something like that. And maybe more importantly, how can we make a prediction without necessarily seeing what that graph is going to look like? How can we make a prediction from the equation? Okay? We're going to use the e-tool from 7-2, and to get to this, I already have it pulled up, but to get to this, we've got in our ebook, right? You can see me here. I'm in section 7.1.1. Here's question 7.1, and we've got the two graphs I just kind of circled from our notes. And again, if it's not abundantly clear, those are nonlinear functions. And one of the things that makes them nonlinear is because the rate of growth is changing. And we can see that here in 7.1. We've got y equals mx plus b. There's our slope-intercept form of a line. And then we've got the equation of an exponential model in its apparent form or simplest form, whatever you want to call it. Notice what that x looks like. That x is in the exponent. It is representing that repeated multiplication, indicating that we are growing by a different number every time, right? We're growing by the value of that base, or a multiple of that base, every single time. So that's going to be a pretty important takeaway, and it's why we get a curve out of that. And our job with the help of this e-tool is to investigate what these graphs looks like. And we've got 7-2, and it does say part 1. We'll get to part 2 in the next video. And it says to do this with your team. We, of course, are not with our team. That's why we're watching the video. But we're trying to figure out how many different graphs we can get and maybe start to scratch the surface on what they look like. So I just click on this e-tool right here, and it brings up this. And the really cool part about this e-tool, and I've got an exponential growth function, and it looks great. I'll just say that outright. But they give me, and I'm going to just change this. I'm going to make this red, and I'm going to go to projector mode so it stands out for the purposes of the video. They give me the growth function, and it looks great, but it's very, very basic, and without some context, exponential growth graphs may not get more exciting than this. But here's why this e-tool is really, really cool. in Desmos, they've built in a slider, and this is not a hard thing to do, and you might be able to very likely figure out how to do this on your own. But they give me a slider, and I can adjust this base. Remember, this base is the thing that I'm multiplying. I can make it larger, and I can make it smaller, right? We started with it at 2, so I'll go back there. But look at how that graph is changing. Okay, look at how that graph appears to like kind of steepen up toward the end as I increase that B value. Okay, and here's the beauty of the slider. I can click on this button right here. I can click the play button and watch what happens. All right, I'm going to let that go a couple more times, and I'm maybe going to push you a little bit to see like what you notice or what you could generalize, because by the time we're done with this lesson, the first video and the next video coming, we really want to have an idea of what we can expect. Okay, I'm going to show you a couple examples. We saw where it was 2. I'll try to put it back there. I'm pausing and I'll go back to 2. This definitely looks like an exponential growth function. There we go. Okay, that's where we started. And as I dragged that slider out here, it got a little steeper toward the end. But what happens when I work back this way? It looks like it's getting a little shallower on the end. And then when I drag it back here, I just have it adjusting by tenths. Now when I stop at 1, it's a flat horizontal line. Oh, okay, interesting. Why maybe could we consider that to be the case, or why does that make sense? Well, remember, if you're multiplying by 1 as your base, repeated multiplication by 1, does that change things, right? 1's our multiplicative identity. But watch this. When I drag it down here less than 1, look what happens. Very clear now that I've got an exponential decay model, right? Because I've started very, very large, and now I'm decreasing as I move from left to right on this graph. Okay, looks like a downward ramp or a downward hill, whereas when my B value was here, it was like an upward ramp. Okay, but watch this, right? There's 1. If I continue to work back this way, right, here's 1. If I continue to work back this way, watch what happens. As that graph gets closer and closer and closer to 0, that gets a little steeper, and you might be able to predict where it's getting really close to, but then it turns into 0. What the heck happened there? And then when I drop into the negative territory, the line's totally gone. All right, and it's not like the graph is hiding. I didn't somehow make it disappear just by moving it off the viewable window there. It's gone. Now, why would that make sense? And we're going to try to do some investigating of that as we move forward. Okay. Here we go. We're gonna move on to 7-3, and we're gonna talk about this problem, and we're gonna use Desmos one more time. We've got a function y equals 1/2 to the x power, and I can see the graph, but just to make sure we can utilize a tool to help us do some solving or some critical thinking about some things, I'm gonna go back to just a brand new Desmos window, and it's www.desmos.com, and I'm going to just click start graphing, and I'm going to type this in, y equals, and I'm going to enter it just like they do. Of course, you could type in, 1/2. I got to get out of the denominator, and then to the x power, and here we go. I've got that function that we can kind of see right here in the notes. The window's not the exact same, but you guys can see that, I think. I'll turn projector mode back on so we can see it. And it says, describe what happens to y as x gets bigger and bigger. For example, what is y when x is 20, when it's 100, when it's 1,000, and a much larger number? Okay, now here's what I notice. I see this graph, kind of trending downward as we move from left to right there. And it trends downward pretty quickly. In fact, it trends downward pretty quickly until it gets to the the y-axis here, and then it continues to trend downward, but not as quickly. It's still going downward, and then it like almost looks like it levels out. Okay, now it would be weird if we had this thing trending downward and then it just flatlined. Not impossible. it would just be weird. So here's what we want to check out. I'm going to kind of drift out here. I'm going to zoom in because the first value they asked me about was 20. Okay, and I click right there. And if I'm not careful, I'm like, oh, it looks like it, kind of ends at 0 there. Okay, but I'm going to pause the video. I'm going to link a table to this, and I'm going to show you kind of something really cool that is going on. Give me just a second. Okay, so we're back, and I definitely paused this, and I added a second thing here. I added a table, and the goal of doing this is to really help us see what happens here. I added a table to this, and I'm going to turn this table on, and we're going to make some data show up here. Because when I give Desmos an X value here, what Desmos will do is it'll use this Y1, it'll use the equation that I have this linked to produce a Y value. Now, we saw here when I clicked on this, when it was 20, there we go. When it was 20, it said, oh shoot, it disappeared now. There we go. It says 0. Now let's see if that's actually true. If that's the case, I should be able to type in 20 here and get it to spit out 0. Now, the dot definitely shows up in the same spot, but is that 0? Now let's talk about this. It's not, is it? Right? This is a number in scientific notation. It's 9.53, et cetera, times 10 to the negative 7 power. That is like 0. A decimal point, 6 zeros, and then a 9. That is an extremely small number. It looks like it was 0 here because Desmos did some rounding. The next value it asks about is 100. Let's type in 100 and see what happens. Whoa, that's even smaller. It's still not 0, but it's smaller than where we started here, right? So what appears to be happening is that it looks like it's getting horizontal. For all intents and purposes, it is getting horizontal, but it's definitely not at 0, right? We're getting close to 0. We're not touching 0. I think it asked me like 1,000 next. Holy cow. Look at how small that number is. That's like a 0, a decimal point, 301 zeros, and then a 933. That's how dinky that number is. And then it said something like a really, really large number. Well, let's keep going here. Let's make it 10,000. Okay? And there we go. I think Desmos has reached its limit, and you can see what happens there, right? I've run into an issue where maybe there's a stack related problem, and Desmos now just rounds that to 0. What happens if I type in like 5,000? Right? There we go, 0 again, right? How about 2,000? I got 0 there, right? So you can see that we are approaching that value of 0, and if it weren't for the rounding on Desmos, we would end up at, we would still show getting closer and closer and approaching 0, but due to the rounding, we end up at 0. Does this have an x-intercept? Well, in this particular case, we're going to go ahead and we are going to admit that no, it does not. It's this idea, this conceptual idea that, and this is tough in math sometimes, we are going to get close to 0, but we are never going to touch it, right? It is the idea of approaching a boundary, but not quite getting there. And that's what we see here in C. It says when x is very large, the graph approaches the x-axis. That is, as x gets larger and larger farther to the right along the curve, the closer it gets. X is called the x-axis is called the asymptote. We're seeing this asymptotic behavior from this particular graph, and we will get more and more into asymptotes because exponential functions have them, but the key concept, the key takeaway is to understand that we're getting close to 0, but we're not touching it, so we won't have an x-intercept here. Okay, and then of course, does it have a vertical asymptote? Right, a vertical asymptote, you guys can see that question down here, is like, something that would be up and down. There's your vertical line, and the answer here is no, it's not going to, and that reasoning is, as we back up, as we continue to work from right to left now, that graph is just going to get taller and taller and taller, and it's always going to be increasing. It'll always be increasing at a reciprocal of this rate. And I know that's a tough idea, but it's an idea that we're scratching the surface on and we're going to keep working with, okay? But it will not have a vertical asymptote in this particular case. All right, we've got just a tiny bit of review preview here, ladies and gents, and that review preview you guys can see right here. And remember, we try these things because sometimes we don't know what questions we have until we try that questions were assigned, right? So try these things. Go ahead and ask the questions you have. Ladies and gents, thanks for watching. Have a great day.